מספר מאמרים. חגי זכה לאורך הלימודים שלו במלגות יוקרתיות, הבולטת בהם זה מלגת עזריאלי. קצת על חגי, הוא תלמיד מקסים, הוא מבריק, וזה שותף אל היהודה, הוא עבר על הטקסט, הוא אישר הכל. וסקרן וחרוץ, היה תענוג לעבוד איתו, ואנחנו עוד עובדים איתו, אז כיף לנו. מתמחה בגיאומורפולוגיה נחלית וחופית, נשמע על זה, תוך הבנה של התהליכים שמובילים למה שנשאר לנו בסוף כגיאולוגים ברקורד. חגי ראה יכולות פנטסטיות בתיעוד של הדינמיקה של הגיאולוגיה בים המלח, בנחלים ובחופים, יכולות של מדידה מתקדמות, הוא פיתח מכשירים חדשים שנראה במהלך ההרצאה, והשתמש במכשירים הכי מתקדמים למדידות של זרמים ועוד דברים. גם היכולת של הניתוח הפיזיקלי שלו, הוא יורד לעומק התהליכים, מבין מתוך משוואות שימור, הוא מבין את התהליכים. או כמו שיהודה התגר את חגי בתחילת הדוקטורט, הוא אמר לו, בוא תספר לנו מה דרוש מבחינה סביבתית כדי להזיז חלוק אחד. ואז נבין יותר טוב את הקשר בין הסביבה לתוצרים שאנחנו מקבלים בסוף בגיאולוגיה. הוא עשה את זה הרבה יותר מהמצופה, ועכשיו נשמע.
So thank you, Nadav, for the presentation. I'm excited to be here today and to present my dissertation seminar, which will deal with the fluvial and coastal geomorphology and sediment transport in response to the regional hydrometeorology and Dead Sea Lake level fall. This was done under the supervision of Yehuda and Nadav. And the lecture will be comprised of 3 parts in which great collaborators are involved, as you can see here. In the picture behind, this is the research area that I worked on in the past almost 6 years. And you can see that this area can be taken as analog to what we find along continental shelf and slopes in the world. Imagine that this area is under the water, and under lake level decline, we expose an area that is analog to the continental shelf, a transition to a shelf edge, and a continental slope. And across this landscape, there are geomorphic processes that shape the landscape, like stream incision, sediment transport in the stream, and then the redistribution of the sediment in the basin. Let's have a short tour across this landscape. This is a flight from west to east over the newly exposed shelf. You can see that it's low gradient area comprised of muds. Here the transition to the shelf edge with tiny gullies that incise it. And we can see again this incision of stream across the landscape. We can look on these processes in such schematic diagram, at which we can see a place that the shoreline was located at higher levels. We call it a high-stand shoreline. Along this shoreline, coastal prism is accumulated, comprised of coarse gravels, and so on. And after some time, lake level declines under the hydroclimatic controls, and the lake level is located at time 2 below the shelf edge. And in the first part, I will explore the processes of stream incision and sediment transport and the mechanistic aspects of this transport in the stream. This will be the first part of the lecture. Next, in the second part, I will explore the redistribution of the sediment in the lake. And again, the mechanisms and physics of transport and sorting of the gravels along the shore, and the transfer of momentum from the generated wind into the waves, and from the waves to the actually moving boulders. In the last part, I will take a larger perspective of the processes under the large hydroclimatic control that link the processes in these 2 sediment conveyors. So let's start with the first part. Here I will ask what control incision of streams and the connectivity of coarse sediment transport across the shelf under base level fall. I will say that generally in the world there are no field scale analogs for such setup. The video that you saw in the beginning of the exposed shelf is a unique exposed landscape for the Dead Sea. Now in the rest of the world it is submerged under the water. And specifically in the Dead Sea, most of the studies dealt with the evolution of stream profile, but none of them dealt with the transport of coarse sediments into the basin. For sure, it relates to landscape evolution, climate reconstruction, if we link it to the hydroclimatic forcing. And people are also interested in the sediment piles that are accumulated in low stand deltas at stream mouth, because these are potential reservoirs for resource exploration. Such question was tackled, for example, in lab experiments. This is a flume with sand, for example, and the process is modeled in small scales in the lab, and also explored the submerged geological record of paleo valleys. And I suggest to look on the processes in the Dead Sea, which is in intermediate field scale. We have the processes occur in real time in front of our eyes in a time frame of a PhD research, and also the conditions are well known. The study site is located in the northwestern part of the Dead Sea, in the mouth of Nahal Og, Nahal Kumeran, and we will see a small taste from Nahal Tmarim. And this area is subjected to a sharp gradient in the rainfall. We have mean annual rainfall of more than 500 meters in Jerusalem, and it decreases to less than 50 millimeters per year near the shores of the Dead Sea, and this affects the hydrology and geomorphology that we observe in these basins. Now I will go to have a look on again on this exposed shelf and its geometry. So we're looking on a transect from 0 here is road 90 and 1.5 kilometers to the Dead Sea shores. We can see these three geomorphic domains that characterize the area. The high stand delta domain with the coarse gravels of 2% slope, the low gradient muddy shelf with the very low gradient slope, and transition through the shelf edge to the high gradient slope. And the exposure during the years of this area can be correlated to the spatial evolution of the Dead Sea level decline. So for example, we can see at what time the shelf edge was exposed. You can see that it happens in the late 1980s. And since that time, the high gradients of the slopes are exposed. And this is very important for us because the exposure of these domains serves as the downstream boundary conditions for the streams to evolve in response to lake level decline. And again, you can see the analogy. To explore the processes, I used the LiDAR digital elevation models, aerial imagery. I made lots of measurements of grain sizes, for example, and mapping in the field. And I used the well-known lake level decline with correlation through the elevation in the landscape to date specific. You can see beach steps or beach berm along. These are steps along which gravels are deposited. So this is a direct dating through the lake level decline. And I use all of this data set to explore the evolution of sediment transport in such landscape by means of the Shields criterion, from which we can define the transport evolution. We are looking now again on this area from aerial photo. This is the shoreline of the 1970s and the exposed domains since then with the transitions that I showed. And these two neighboring streams, Nahal Og and Nahal Kumeran, you can see that they respond to the same lake level decline absolutely differently. Nahal Og, just from this picture, is connected with the lake, transporting sediment to the lake shore, whereas Nahal Kumeran is actually disconnected from the lake in terms of sediment transport. And why this happens? So we relate the different responses to the, first to the hydroclimate that characterize each one of the basins. We saw that Nahal Og is a larger basin that is subjected to more rainfall that precipitates over the year. We define it as a rain index, the mean annual rainfall over the watershed, and we can see that it's 7 to 6 times larger in this, in terms of this index, which means that the potential for sediment transport, the geomorphic processes, incision in the stream is much higher here. And the second parameter that we can look on here is the geometry of the exposed shelf in front of each one of the basins. Here we can see that the shelf is twice narrower than in Nachal Kumeran. Thus, this stream maintains the connectivity with the lake, whereas this stream is actually disconnected. And in the field, it looks like that. This is a schematic diagram that shows the response of Nachal Kumeran with braiding of the stream on top of the shelf. You can see the alluvial fan that develops here, and with time, you can see that it's a progradation on top of the shelf. Whereas Nachal Og, this is how its connectivity in terms of sediment transport looks like at the position of a low stem delta. And now I developed the discussion about Nachal Og to see how such sediment transport evolve in time and what are the conditions to transport the sediments from the high stand reservoirs to the low stand ones. And then I will also conclude some insights about Nachal Kumeran. So to do that, we have to look on the channel profiles evolution. So this is again 0 here is road 90, and to the lake shore here at 1,600 meters. And we can see this is the exposed bathymetry that we saw. And with time, after the exposure of the shelf edge at the end of the 1980s, we see that the channel profile steepened with time. They also follow the lake recession and lengthen according to its recession. And the whole channel profile responds to the lake level decline in terms of small nick points that migrate to the upstream of the channel. We call it actually a nick zone. And in this area where the higher gradients of the nick point arrive to the area of the high stand delta reservoir, we actually increase the potential to transport coral sediments from this reservoir to the low stand one. We actually observed the onset of what we call bypass, sediment that are transported from upstream to downstream in 2001. Now we can look on this data in another representation. We call it a spatiotemporal diagram, because here the y-axis is time from the 1970s to 2016. And the x-axis is exactly the same axis like here. And first thing that I plot here is the coastline retreat of the Dead Sea, so the exposure of the high stand delta, the low gradient shelf, and the slope. And into this diagram, I can plot some parameters. I will start with the first one will be the slope that we can obtain from these profiles. So I'll take one example to try to explain how it works. So you can see here the first profile is the actually exposed bathymetry. So the shoreline was here at the end of the 1980s. You see the shoreline here. So here I cut the diagram at the end of the 1980s, where exactly when I exposed the shelf edge. And I plot the slopes. These numbers are slopes over the diagram in terms of these contours. Now I complete the evolution of the stream with time, and you can see, for example, that in the beginning, the channel incised into the high stand delta, and thus the channel gradient decreased with time. However, after the exposure of the shelf edge, higher gradients migrate from the downstream to the upstream, as we can see here, and the higher gradients in darker colors get into the high stand delta domain and increase the potential for sediment transport. So this is how this diagram works. So this is again the slopes diagram. I did the same exercise for another parameters, for example, the channel width, and using the mass conservation formula and Manning formula and an estimation for a typical flood in the channel, I could reconstruct or estimate a water depth in the channel, also presented here on this spatiotemporal diagram. Having in hand the slope and water depth, I can now start to calculate the potential transport for different classed masses according to the Shields parameter, which is actually the ratio between the bed shear stress and particle weight. And let's see how it looks like. The potential mobility is taken relative to a critical value, which is defined according to different models. Here I will show the one that fits with our observations. Let's start with an example from the smaller clasts that are observed in the field, from the 0.1 meter clasts. I plot the mobility and immobility fields on this diagram. So immobility is the white areas and mobility are the gray areas. And you can see that for this smaller clasts, they become mobile across the entire shelf since the early 2000s, according to Ashworth model. And we actually observed them along the abandoned fan delta and shoreline that you saw in the previous picture. The same happens for the larger clasts that are observed in the field. But you can see that because they are larger, heavier, the potential mobility for this clast is observed only later, during, for example, here, 2010. They are able to be transported from the high stand delta to the low stand. And these are the shorelines that we see in the field, in the mouth of Nahal Og. The evolution of this low stand delta show us actually gravel coarsening from the early 2000s till today. And it's actually sorting of the sediments that build this low stand delta. This is how the measures of gravel Dmax looks like with time, with the two examples that I showed. And also we see this onset and intensification of the sediment bypass across the shelf in terms of increased sediment volumes that are transported to the channel mouth. And this is maybe the first time that we observe such process in the field with all the details. And we have the agreement. It's important to say that we have the agreement between the theory, the basic theory of the shield's evolution of sediment transport and the observation in the field. I will conclude and say that we saw the exposure of a certain geometry of the shelf and slope under lake level decline. Channel profile started to evolve after the exposure of the shelf edge, and with the shield's parameter relative to a critical value, we saw both through this parameter and in our observation how the grain size increase with time and the volume increase and generate such a low stand architecture. I will just go back to, this was what we call the Og type, the fully connected type of stream, but we saw also the neighboring disconnected stream under the effect of different hydroclimatology and shelf geometry that this stream encounters. And I will say that we find the analogy, for examples, in the streams or rivers that drain into the Gulf of Mexico. We see such diversity in the responses of streams to base level fall. And the discussion is long about it, but I will not expand it here because of the limitation of time. And I will continue with the second part that deals with the sediment. We get an unsorted sediment pile in the mouth of the stream, now waiting for the hydrodynamics of the lake to transport and sort these sediments and reorganize them in the lake. So in this chapter, I will focus on the transfer of momentum from the wind that generate waves, and then waves that attack and provide momentum for the boulders to be mobile along the shore. Specifically, I will ask what is the wave height required to mobilize a given class mass, related to Yuda's question from the early PhD stages. What is the longshore displacement of a class under the action of a given wave? And how does the distribution function of the storm wave heights govern the longshore gravel sorting? Here, again, we are talking about coastal evolution and also coastal management, especially during days of increased storm frequency and intensity, as we know. Coarse clastic beaches are very common over the world. We can see them along oceans, in lakes, and also as artificial boulders that are placed along shores to prevent erosion. And the problems and sediments in such setups are mixed, always mixed. They arrive at different times and mixed along relatively stable level shorelines. And thus the sorting signal along the shores is weakened. So I will show you what happens in the Dead Sea. This is a storm that I documented, actually the largest storm wave that I documented in my dataset. These are waves that reach up to 4 meters in depth of 10 meters measurements of the Dead Sea. You can see what happens along the shore. It's a violent, turbid environment, and we don't know what happened here under the water in terms of sediment transport. And this is a problem not only in the Dead Sea, but anywhere else. Thus, there is no monitoring of intrastorm measurements of boulder dynamics in general. And thus, also the physical understanding of the process, of such processes is limited. So to answer this gap, we developed what we call smart boulders. So this in the picture, and we have one here for example. These are boulders. This is the smallest one that I colored, weighted, numbered, and drill into these boulders a hole. Inside this hole, we install inside such watertight housing an IMU sensor. This sensor records accelerations and rotations in 200 hertz, and actually can give some sense for the boulder motion in real time. And such boulders were placed in the coastal environment before storms and were picked up after the storms. Then we have data of boulder motions. Also, to increase the statistics, I colored, measured, and weighted other boulders, placed them in the channel mouth or along the shore, and could measure after a storm the total longshore transport of these boulders. Here there is a movie that me and Dido are coloring some boulders in the field. And for the forcing of this process, I have measurements of a meteorological station that measures wind, speed and direction, temperature, relative humidity, and most important, lake level and the waves by an underwater pressure sensor. I also complete this data set with some data from the Israel Meteorological Survey. And at specific storm, we install underwater measurement array that measure, for example, by acoustic Doppler current profiler, directional waves and turbulence. I also use, to get some more observations, remote operated vehicles and special watertight cameras, and for the subaerial documentation, also photography and photogrammetry with a drone. After collecting all of these observations, to understand the relations between the parameters and get some insight, I use the shallow water linear wave theory to give us a theoretical framework for the process. So I'll try to convince you that in the Dead Sea we have a very clear setup for the coastal sorting. So this is how this shoreline looks like. You can see one shoreline, then a separation, and another shoreline. And this is actually a time series. And this time series can be seen through first the lake level decline, which is relatively stable during the winter and significantly falls during summers. Then this is wind speed. We can see that most or all of the wind storms are focused in the winter, whereas the summer is calmer. The wind direction, here in the black dots, according to the azimuth, so 0 and 360 is north, and 180 is south, so winds are bimodal, southern winds or northern winds. And when I say southern winds, these are winds that blow from south to north. I filter this wind directionality according to the wind speed, and you see in the orange dots that always the wind storms are of southern winds. This means that they will generate wave storms. These are waves scaled between 0 to 1, and 1 is the 4 meters wave height that we measured in the strongest storm. And this wave propagates from south to north and generate the unidirectional transport that we see along the beaches in the northern part of the Dead Sea. And also this explains us the separation between beach berms and preservation of sorting, because we deliver sediments through the fluvial system during the winter and redistribute them along the shore under this section of winds and waves. Then during the summer, lake level declines at about 1 meter, and here we start to generate a new shoreline. So we have separation and preservation of the sorting. And again, this is how it looks like. And to convince you that we see some sorting, this is the channel mouse in 0 and grain size that I measured. And we see that how it decreases here along A to A tag, decrease away from the channel mouth in terms also of Dmax and D50. When we look on this control area, we can see how this coastal conveyor is arranged. This is the active shoreline in blue, and it's a narrow strip that extends between 20 to 30 meters wide and up to depth of 2 to 3 meters. And we can see that because of the angle of the coast at about 45 to 50 degrees and the propagation of the waves from south to north, we can see how the wave attack the beach at 45 degrees and generate an optimal, maximal longshore transport of the boulders. And this is a cross-section that can show the seasonal steps, beach burns, the transition into the coastal conveyor. And let's have a look how it looks in the underwater environment with our ROV. So these are the boulders. Sorry for the noise. These are two smart boulders waiting for the storm to arrive, and one old yellow boulder that was transported in previous storms. And we are at a depth of about 1 to 2 meters, following this cable up to depth of about 5 meters. We can see here the transition to an area comprised of ripples, of sands and silts. And this is our measurement area at depth of 5 meters that measured during the storms. It was a bit noisy. And now let's have a look. These are several campaigns that I will present some results from. We will start from this campaign that I used these smart boulders. This campaign was conducted at February 2020 with 5 smart boulders with different masses. This is the smallest one, number 1 here. And along 10 days, these were the wind speed, and we can see the directionality of wind in terms of azimuth. These are southern winds, as expected. The waves that were generated, also purely southern, as was measured independently by the ADCP. And these next 2 panels are very important. Here I show the accelerations, the resultant accelerations and rotations for all of these smart boulders together, and I follow the same color coding. And simple insights from this graph are first that the movement occurs under the action of waves. Currents, I will tell you that currents are not a factor here, and also that it happens at a very short periods of time, only during these storms, during the winter. I analyze this data set and actually classify the state of motions of the boulder into 3 categories according to traffic light colors. So red, no motion, yellow, pre-motion, and green motion, and how it works for each one of the boulders. I will give you an example from the rise of the storm for one of the smallest boulders. Again, the resultant acceleration and rotation presented in the black dots, and the wave height is the blue curve. And we see that there are no deviations of the sensor noise when I classify the motion as no motion. There are slight deviation from the sensor noise in both records, but mostly here it's important to look on the acceleration. And I define it as a pre-motion stage. And when I see significant deviation, especially in the gyroscope, I define it as initiation of motion. And this transition from yellow to green is very important because at this point I can define the initiation of motion of a specific class. I did this exercise for each one of the boulders several times in the transition between the storms and for each one of the masses. And I got this very special relation between the critical wave height to the boulder mass. So we have here a first observation for such relation in a coastal environment. This is one of the things that we are proud of in this work. But even achieving such relation, we felt it's not enough because we still don't understand the process. We don't know what relates these dots. So in order to do that, in parallel, we developed a theoretical framework based on a shallow water wave theory. And we considered a submerged boulder that experiences the hydrodynamic wave force, which actually stems from the fluid pressure over the boulder. And we can see that this drag force scaled as the squared wave height, which comes from the velocity of the medium, that acts on the surface of the boulder. This is the characteristic diameter of the boulder, and this is how it looks like in terms of wave height and boulder mass, because I talk about boulder masses. The force that prevents the boulders from moving is the friction force, which scales the boulder mass. And now the condition for incipient motion will be that the drag force should overcome the friction force. When I do the algebra for these two scaling relationships, I get that the critical wave height should behave as the mass to the boulder of 1/6. I will just mention that we kept and analyzed also all the prefactors, and we know how the period of the waves, the sediment and fluid densities, and water depth, and drag and friction coefficients are involved in this formulation. And here I plot our new relation on the data from the smart boulders, and we see a very nice fit between the observation and the model. And again, here we were very excited because this gives us a first sense for the sorting of the boulders along the beach during the storm ride. This is the theoretical relation of how the boulders will be arranged. And also it have an important implications for coastal management and stability of cobbles boulders along shores. This was the first step. And now we want to move one step forward. So we took our relation and we wanted to understand how much a specific boulder will move, what is the distance that each boulder will move under a specific wave. So here it's a theoretical part that we will consider the movement under the action of a single wave. Here we consider the wave impulse that is exerted on the boulder and result in the change of momentum. It transfer velocity. The boulder is moving now, and we can say that the velocity of the boulder scales as the displacement per wave. And this is how these terms look like. We also keep everything from the prefactors. Let's see what this relation means. I will show it on this diagram of wave height on the y-axis and boulder mass on the x-axis. This is the first relation that we developed. So no motion in this area, and this line is the incipient motion relation, the first relation. Then the second relation, I will plot on this part the movements of different mass boulders according to their wave height, where these numbers are different displacements of the boulders. The darker the color is, the longer is the displacement per wave height. Let's see what this diagram tells us. So let's consider a low energy storm, for example, of 1 meter wave height. We can see that for 1 meter wave height, for different masses of boulders, when you go here to the right, we don't get separation between lighter clast and heavier clast, right? However, when we consider a higher energy storm, for example, 3 meters wave height, we see how we cross these lines of the diagram, and the separation between the especially the lighter class from the heavier class is very significant. So under a high energy storm, we'll get much better sorting along the shore, which will behave according to this physics. So now we have in hand the physics of motion, and we can go forward to the last step that I'll present and what happens with the sorting under the action of a full distribution of wave heights during a storm. I will give example from the storm with the yellow colored boulder. This is the wave height distribution. Wave height here counts here. The wave height distribution for us is the wave climate. It resembles the regional wave climate. We approximate the behavior of the wave height distribution to a power law, h to the power of minus capital N. And this works for another storm, for example, the color with the red coloring. And near to the wave height distribution, I plot now the measurements of coastal sorting, of the total longshore displacement of different masses of boulder that we measured. And we can see that it can also be approximated to behave like a power law. I would just say that in logarithmic diagrams, the power law it looks like a linear line. And also for the other storm. And now the big question is, what is the relation between these two worlds, the wave climate and the coastal sorting? And to understand that, we actually integrated the single wave displacement from the theoretical part in the previous stage over the wave height distribution from the critical wave height and up to infinity. And we got from solving this integral that it also behaves as a power law, very similar to that, the mass to the power of alpha. Again, the big question now will be, what's the meaning of this alpha? So we get that the meaning of this alpha is that, and you can see that this n that is colored here in green, which actually the exponent here is the slope, right? Is the slope of the diagram. It enters directly into this alpha, so it determines the slope of the diagram of the coastal sorting, which means that the wave climate, how the waves behave during the storm, will determine how the boulders will be arranged along the shore and will be sorted. So we have a very important relation between climate and sorting, or climate and geomorphology, and it's a desired goal for all of us. So I'll conclude that the coastal storm scale sorting is dictated by we saw initial mobilization of respective class mass, which develops according to the temporal evolution of the storm, this exponent n. The average displacement of class per wave, with sorting intensifying with class fining and increasing storm intensity. And the wave climate that is encapsulated in the sorting of coastal landforms. And last, we saw that the wave hydrodynamic pressure-induced force and impulse govern the physics of these motions. Now we saw actually the mechanisms and physics, transfer of momentum, both in the fluvial conveyor and both in the coastal conveyor. And we're ready to actually go for a larger scale of the synoptic scale hydroclimatic control over these processes. And in this part, I will ask, how does the fluvial and coastal interaction generate a specific geomorphic architecture? What are the characteristics of atmospheric circulation patterns that activate these conveyors? And what can we learn from the modern environment into past geomorphic records? Again, the challenge here is, for example, to link processes that occur over a range of spatiotemporal scales, from the hydroclimatic synoptic control, which is a large scale, to the boulder scale that moves along the shore, and a relation of chain of processes that are often studied in the literature separately. Here we take the entire range of processes. So we'll give example for one storm, at which I will show the representation for the coastal sediment conveyor and the fluvial sediment conveyor. This is the storm of the yellow colored boulders. These are the wave heights. This is the wind that generates the waves. The axis is reversed, don't be confused. With the directionality in the black dots, we know that it's southern directionality. And boulders were moved, lighter boulders were moved up to 100 meters along the shore, and heavier ones about 10 meters along the shore. Whereas in the fluvial conveyor, we can see that after the peak of the waves and the winds, a rainfall start to develop, here in millimeter per hour. Also, the axis is reversed. And it generates this flood. This is an estimated hydrograph from our time-lapse cameras. It's a relatively low discharge flood, but even under this flood, yellow colored boulders not yellow, but colored boulders that were placed in the upstream near Road 90 were transported across the entire shelf about 1 kilometer to the stream mouth. So this gives us a sense of the transport rates in the stream and coasts. And how the synoptic circulation during the evolution of this storm looks like. So we look on sea level pressure maps that were generated from the ERA 5 reanalysis model. The contours here, the closed contours here with blue line resembles low pressure. And the arrows are vectoric arrows that represent the wind, directionality, and speed. We can see that in the onset of the storm, a synoptic low is located in the area of Greece or Italy, and very calm winds in the area of the Dead Sea. This is the black dot here. During the peak of the storm, which is aligned with the peak of the wind, we see that that the low migrates eastward, focuses and deepens, and stronger winds arrive to the area of the Dead Sea with southwestern directionality, where the measurements are of only southern winds. This is how it looks like from a satellite photograph, the cyclonic circulation of the clouds. And in the end of the storm, everything calms down, and a high pressure system occupies from the west, and the storm ends. And I will tell you that I analyzed, from my 5 years data set, I analyzed almost 130 storms, and 80% of them behave roughly similar like this storm. They are Mediterranean cyclones that activate both conveyor, the fluvial and coastal conveyor. So the action here happens under the effect of Mediterranean cyclones. And let's look how this 130 storms looks like. We look on a graph of the axis are duration of the windstorm duration versus the storm wave duration. You see that all storms, all dots here are aligned along a one-to-one line, which means that the duration of windstorm and wavestorm are the same. The system is very responsive when windstorm rise, wavestorm rise, and vice versa for the decay of the storm. So this is in terms of duration. We can see the energy of the storm wave by means of the size of the dots. So each dot here resembles the energy of the storm. So we can see that this area of the graph is an area of long duration and high energy storms. And the coloring of the dots here in blue resembles the synoptic classification. So the high energy long duration storms are Mediterranean cyclones, as expected. Almost everything is Mediterranean cyclones, but specifically the short duration and low energy storms are of the other synoptic classification that we explored of Red Sea troughs, Persian troughs, and Sharav lows, and they actually have no effect or insignificant effect on the geomorphology and sediment transport in our region. So this is very important because it shows us the respective effect of Mediterranean cyclone both on the coastal conveyor and the fluvial conveyor. I will not expand the discussion on the generation of rainstorm or floods. I will just say that we found very similar results to what was found in previous studies, for example, by Moshe Arnon. And I will show now an overview of the area and explore the wind regime during the storms that I analyzed. So on a north-south transect on the along the Judean highlands, we can see the winds in these wind roses during the storm in Jerusalem, Rosh Tzurim, and Arad. And you can see that they are almost purely westerlies with a slight southern component. Whereas during the same storms at the same time inside the Dead Sea Rift Valley from north to south in Og and Gedi and Sdom, we see the pure or with a slight western directionality of the same winds. And we attribute this change of directionality in the same storms to the funneling of winds inside the elongated, deep Dead Sea Rift Valley. So here we get a sense to the generation or a delivery of moisture by the synoptic westerly that results in flood and sediment transport in the streams, this blue part. And on the same time, or roughly on the same time, the generation of winds that generate waves and then sediment transport from south to north along the shore. This is how it looks like in the mouth of Nahal Og. We see the transportation in these bright areas north of the channel mouth. We can see just some sediments south of the channel, but most of the this asymmetric sedimentary body is organized like that. I will tell you that I observed this setup not only in Nahal Og, but in other modern streams of the Dead Sea, but I will go even more to the past. To give you an example from the mouth of Nahal Tmarim, its fan delta and shorelines were deposited during the lowering stages of Lake Lisan. And we are looking now to the west. This is the waterfall of Nahal Tmarim, and this is its fan delta. And I don't know if some of you can recognize an asymmetry in the deposition, so I will help you. This is roughly the late Pleistocene fan delta of Nahal Tmarim. Let's now have a look from the LiDAR perspective. So this is the western escarpment of the Dead Sea and the outlet of Nahal Tmarim. And you can see that most of the fan delta is deposited asymmetrically to the north, with the northern part is 4 times larger in area than what we find in the south. And for me, it means, and I see it in other streams also neighboring to Nahal Tmarim in this part of the Dead Sea. And for me, it means that this regime of Mediterranean cyclones that provide the moisture to generate flood and then transport the sediments and arrange them in this asymmetric architecture of the fan deltas and shorelines may have also persisted during the late Pleistocene. This is Yehuda along this sorted beach berm of Nahal Tmarim. And I will conclude now that fluvial and coastal conveyor are activated under the same Cyprus or Syrian laws. The western synoptic winds activate the fluvial conveyor. We saw that the southern orographically funneled winds generate waves that trigger the northward longshore sediment transport in the coastal conveyors. And then in the geomorphic records, regressive shoreline are preferentially deposited north to channel mouth. Today and in the past, and for us this is how hydroclimate is encapsulated in geomorphic records. So this is the end of how I explored such setup that responds to base level decline with the fluvial and coastal processes under the large hydroclimatic control. Thank you very much. Special thank you for Nadav and Yehuda for everything during these years. It was wonderful. For the research collaborators, for the many friends in the help in laboratory and field, for insightful discussion and support for many researchers from here and from over the oceans, the GSI team, and the administrative staff in the GSI and HUGI. And last, thanks for the endless support of my family and of Ataya. These are the fundings of the research, the papers that I published, the papers that I collaborate with, and I will be happy to take questions.
Okay, thank you. Questions?
Question about the second chapter, the longshore sediment transport. And you said that part of the applicability was to move to other settings globally, other shores. I know that your group that did a lot of work on the salt deposition, the salt dynamics along the shores. And my question is, does the precipitation and dissolution of seasonal salt on your boulders, does that can somehow influence the measurements that you made in terms of shear stress?
Yeah, so it's a good question. What we see in terms of salt precipitation is especially in the beginning of the winter when everything was frozen for about half a year during the summer. We come after the summer and there is this sea spray that precipitates salt over the boulders and make a very strong cover that actually blocks the boulders from moving. And then during the end of November, early December, we get the strongest storm that opens the winter, the very strong wave storms that actually break this salt cover. So maybe during the first, especially during the first 1 or 2 storms, there may be some effect on the boulder mobilization. It will take longer to set them into motion. But after that, when the coast is free to move, it should follow the considerations that I presented. But this is what we see, especially in the beginning of winters.
Anyone? So I have a question about the fluid density. So density is at the same line, obviously, and that makes moving and initiation of movement much easier for the boulders.
Yeah, the submerged weight is lighter.
Right, so my question is, in the scaling, where does the density come in?
So I will show it to you.
And then follow-up question would be how would that scale or how would that influence implications for regular coastal regions?
Yeah. So you can see here in the, so first you can see from your questions, according to the parameters here, that the submerged weight of the boulders, this is the relative, the difference between the sediment density and the fluid density. So it will enter here. Okay, and you can see that here this G tag, we call it the reduced gravity, is involved in the prefactor of our formulation. Okay. So it means that it won't affect the scaling laws that I showed, but it can move the graph up or down. Okay, and again, you can choose the Dead Sea, or you can choose an ocean or a sweetwater lake, and it will come into account through this part of the formulation. Okay.
Anyone here? Anyone on Zoom? Maybe? יכול להיכנס לראות בשאלה?
בהצלחה.
I have another question on that. You said you used the linear theory to derive all the equations, but close to the shoreline where you saw the sediments move, it's turbulent flow. So how does that play out here?
So it's a very good question. Actually, because we consider it as a linear wave theory, also the transformation from the waves that are measured a bit to the offshore at 5 meter water depth and not 1 to 2 meter water depth. We assume that also the transformation of the waves is linear. Okay? So, yeah, exactly. So again, the scaling laws should be kept according to the linear wave theory, and we can get some differences that will affect the prefactor. Okay, so this is why also we focus here on the scaling laws, and also show in our diagrams the fit of the scaling laws to our observations, and don't say, okay, we know this part very well. Okay.
Many shorelines, some shorelines, we find well-rounded clasts composed of lithologies that clearly arrive from the eastern side of the Red Sea. Is there a way to explain that within the framework of the model?
So I hope that yes. I haven't explored that. I know that you are very interested in such a class, but for sure, in future work, we have to go also to the shorelines of the Dead Sea in the southern part, because I assume that such clasts should arrive from this direction, for example, from Nahal Arava, and then to see how the wave regime behaves there, and if there is some option that even that you are located in the southernmost part of the lake, you will get some sediment transport to the north and start to move these sediments from there and along the shores. I don't know where you if you know to say a specific point in the northern part of the Dead Sea that you find such a cluster.
Sure,
Of not, yeah. So, yeah. So they had to arrive somehow. So, yeah, but definitely we can explore in future work things that are related to such question.
This is mind blowing. So if you're saying if you keep the lake level stable, so same shoreline, you can actually move within the framework of what you're saying.
Theoretically, you can move, really, really long distances. Yeah,
I blocked the Jordan River.
I will just say that we stopped here the analysis in the framework of a single storm, and we, again, if we are talking about future work, so we have to expand this analysis to multi-storm analysis, and there other factors get into the consideration. So theoretically, yes, but we have to do the work to generalize it.
Okay, so let's thank Haggai again.